want to talk to you about my PhD research. I just finished my 4th year at UVA. I'm a student of Julie Bergner's, and the topic that I'm working on is rational complete Segal spaces. I want to tell you what they are, and primarily I want to motivate why one would care about these gadgets and how they arise and why I'm working on them. So I guess kind of without further ado, I want to start off with, I suppose we can call it section 1, which is a little bit of motivation. And please let me know if you have any questions, or I'm checking the chat as well. And or if like something is illegible, for example, things like that. So motivation, I usually do this kind of small table where, so the rational, this adjective refers to rational homotopy theory. And the complete Segal spaces, they are a way to model and understand, shouldn't have written that, categories up to homotopy. So structures that they want to be categories, but associativity or unitality of composition doesn't hold on the nodes. So categories up to homotopy. So a bit of motivation for the left-hand component, rational homotopy theory. What rational homotopy theory does is, well, you start on one side with difficult problems in geometry and topology. And the idea is that very often, if you sort of discard the torsion that goes on, which is done by, well, tensoring over Z with the rational numbers, so this is where the rational business comes in, you get a problem in algebra, things like rational DG-Lie algebras or co-algebras that might be more tractable. So an example of that is due to Serre from 1951, who managed to compute the rational homotopy groups of spheres. So the homotopy groups of spheres, once you tensor them with Q, to kill off the torsion. So rational homotopy groups of, I'll just write Sn. Whereas you can contrast that to like the usual homotopy groups of spheres, which are very hard to compute, but this result basically tells us conceptually that the difficulty is kind of concentrated, the computational difficulty is concentrated in the torsion information. When you tensor with Q and you remove torsion and you just keep the free part, things become friendlier. So that's some motivation for rational homotopy theory, but I understand this is more of a categorical audience, so I do want to focus on the right-hand side, categories up to homotopy. So what's a situation where you have a structure that wants to be a category, but you don't have associativity and unitality on the nodes, but up to a notion of deformation that is natural in that setting? Well, that arises if you try to view a topological space as a category. So let X be a space. Usually in this talk, a space for me will be a simplicial set, but here it kind of doesn't make a difference. So you can try to define a category with objects of X being, well, that's going to be a small category, or an attempt to define a small category. The objects of X are going to be, well, it's going to be a set. It's going to be X as a set. It's going to be the points of X, and morphisms being paths. So morphisms, that should look more like an O, being continuous paths between points. And your notion of composition is going to be path concatenation, but path concatenation is neither associative nor unital on the nodes. It is only associative and unital up to path homotopy, which is the natural notion of deformation that you have when you study spaces. So this attempt does not, strictly speaking, give you a category, but it gives you a category up to the notion of deformation that one would expect in the topological setting. So the problem is now, like, so you want to find a way to rigorously define and study structures of that form, structures that are categories, but only in kind of a looser, weaker sense. So to finish up what I was writing, but not associative or unital. So the question is, how do we, to kind of transition to maybe the details of what's going on, how do we model, in a sense, such structures, categories up to homotopy, and how do we go about studying? And a good way to motivate the approach that was put forth by Rezk in 2001 is to produce kind of a useful description, a useful way to describe usual categories, and then find a way to kind of weaken that description to get a description of structures that are categories up to homotopy in that sense. So I'll just maybe create a new page over here. So add a page. Do people, I should say, do people have any questions at this point or anything they want to ask? Look at the chat as well. Okay, so let's go to the next section, which is, we'll call it the Segal condition, because this is really the thing that we can weaken, in a sense, and get our description. So the key point here, in the key observation to make, is that simplicial sets, and if you haven't seen simplicial sets, you can think of simplicial complexes, where you have like 0 simplices, 1 simplicity, etc., and faces that take you from higher dimensional simplices to lower dimensional ones. But the new data for a simplicial set is you also have degeneracy. You can view a lower dimensional simplex as an honorary higher dimensional simplex, and that makes kind of makes a very good difference. But simplicial sets, you can think of them as simplicial complexes or spaces. So the thing with simplicial sets, the reason why we're working with those things in this setting, is that simplicial sets, they encode categories as follows. So let's see how we can use simplicial sets to encode categories. So you can, let's let n greater than or equal to 2, and let's take x be a simplicial set. Then the key observation to make is that we have a particular kind of inclusion of simplicial sets, which is called the spine inclusion, where what do? You take the standard n simplex and you include, well, it's one skeleton, if you like to think of skeleton, or if you want to be more visual, you include the following subcomplex where you just keep the one simplicity. So you go from 0 to 1, you go from 1 to 2, yada, yada, all the way to like n minus 1, and then to n. This is called the spine of delta n. So you include the subcomplex, and what it does is it induces, well, to be precise, by applying the functor hom in simplicial sets blank x, well, what it does, it induces what's called the nth Segal map. So that is a set map, which goes, let's call it phi n. And what it does is it goes from xn, from the n simplices of x, to an iterated pullback of one simplices along their 0 simplices. So it's going to be an n-fold pullback. So you have n such things. And this is called, I should say, the nth, Segal map of x. Maybe I should move it a bit to the, hold up. That's not what I meant. Scroll down. Okay. So we can use these inclusions to induce that's a set map. And we can use this set map. So what it does is it takes an n simplex and it restricts it along its one skeleton. So you look at one simplices joined together at like their common face, their common 0 simplex. And we can use these Segal maps to describe precisely when a simplicial set is the nerve of a small category. So let me go to a next page so that I have some room to write that. This is I'll call it the proposition. I can give you a reference if you want, but it's a nice exercise if you care about these things, which says, so let X be a simplicial set, and then the following are equivalent. Number one, there is a small category fancy C such that X is isomorphic to the nerve of C. And number two, for every n greater than or equal to 2, that n Segal map is a bijection or an isomorphism of sets, if you like to think of it like that. So these Segal maps describe precisely when a simplicial set is the nerve of a small category. And the idea is, well, from 1 to 2, you can that's something you can check that the nerve has that property. From 2 to 1, if you have a simplicial set, and this is called the Segal condition, I should say, sentence 2. This is Segal condition. And now if you have a simplicial set that satisfies the Segal condition, you can kind of follow your nose. You can say, okay, I'm going to define a category, small category, whose objects are x0, whose morphisms are x1. And then the second Segal map being a bijection gives you a unique composition. The third Segal map being a bijection makes it associative, and you can check unitality, and you get a well-defined category. So we can use simplicial sets and the Segal condition to encode categories. And now this gives us a nice hint about how to encode categories up to homotopy. So this leads us to complete Segal spaces. And well, the problem is that in our setting right now, because phi n is a map of sets, there's no natural way to weaken the notion of a bijection for sets. But if phi n was a map of spaces, so if we were working with simplicial spaces, or to be more rigorous, in my case, bisimplicial sets, simplicial sets, then we could say that phi n, we could ask that phi n be not an isomorphism, but something weaker in spaces, namely a weak homotopy equivalence. And that turns out, thanks to the work of Rezk, turns out to be a very good way to describe mathematical structures that are categories, but only up to homotopy. So let me write down and this is called the complete Segal space, the definition that I'm going to write down. So it's due to Rezk from 01, his paper, a model for the homotopy theory of homotopy theory, which says that a complete Segal space is, well, let's just call them maybe simplicial space. Technically, I mean bisimplicial set. So it's a simplicial space X such that, well, first of all, you want that for all n greater than or equal to 2. Now phi n is going to be now a map of spaces. So you want it to be a weak homotopy equivalence. And then you have some other technical conditions that I don't need to get into, but for the people who see these things, the other technical conditions are number 2, you want this simplicial space to be Reedy fibrant. You want it to be a fibrant object in the Reedy model structure of bisimplicial sets. And number 3, for the complete part, there is a way to formulate a completeness condition that you also need, but I'm not going to be using that explicitly. Kind of the main takeaway is that now you ask that the Segal maps be not isomorphisms of, well, in this case, spaces, but because you're working with spaces now, you ask that they be weak homotopy equivalences. So this turns out to give you a notion of morphism composition that is well-defined and associative and unital, but only up to a notion of deformation. So this is a way to model categories up to homotopy. And Rezk, what he also does in that paper, is he kind of puts forth a very systematic way using model categories to study these things. And that revolves around the following theorem, that kind of summarizes some of his main results in his paper about complete Segal spaces, so Rezk 01, which says that, well, there's a model structure, which in the sense of a Quillen model category or closed model category, he denotes it by CSS on simplicial spaces. And that model structure is given by a Left-Bowski localization of the Reedy model structure, if you're familiar with that. And in that model structure, the fibrant objects are the complete Segal spaces. And I should also say that also this model structure, this model category CSS is what's called, that's an important property, that it is Cartesian. So Cartesian, maybe I think it's written usually with a lowercase c. Cartesian, what it means is that it is compatible with the Cartesian closure of the category of simplicial spaces. And this Cartesian closure, what it means, or maybe the most important takeaway, is that if you have two simplicial spaces x and y, you can form an internal home. You can exponentiate. You can talk about x to the y, which is going to be another simplicial space. So you have like a simplicial space worth of maps from y to x. And this model structure is compatible with this exponentiation, with taking internal homes. This corresponds to like a bunch of technical axioms. So this is a nice kind of way to study these things. You put a model structure where the fibrant objects are the things you care about, and then like fibrant replacement gives you a way of replacing a random simplicial space with something that you like up to a weak equivalence. So my project revolves around defining what I'm about to introduce right now, which is rational complete Segal spaces, and which are at the intersection of rational homotopy theory and categories up to homotopy. And what they describe is categories up to homotopy that are enriched not just in spaces. You don't just have a mapping space between any two objects, but that are enriched in rational spaces. You have a mapping space between two objects with higher homotopy groups, are not just abelian groups, but the rational vector spaces. You can uniquely divide homotopy classes. And that sits at the intersection of rational homotopy theory and categories up to homotopy. But let me give you the precise definition to get to like the new work that I've done. So that, I guess it's section 4. So rational complete Segal spaces. So the notion of rational that I was working with, I should say, is due to a paper of Gomez-Tato, Alperen, and Tanre, who are doing rational homotopy theory for not necessarily simply connected spaces in their paper from 2000. And we say that a general space which need not even be path connected. So for a general space, a space X, we say that it's rational if, well, with respect to any choice of base point, is what I mean, for all n greater than or equal to 2, if you look at the nth homotopy group of X, it's not just an abelian group, but it has the structure of a rational vector space. So you can uniquely divide any homotopy class by any positive integer, which is like multiplication by 1 over n. So that's our notion of a rational space, because if you take a random simplicial space and you look at its like 0 simplices or 1 simplices or 2 simplices, they need not be simply connected. So you need to have a notion of a rational space without any connectedness hypotheses. And this is the one that I'm working with. So with this notion of rational, I can define what my notion of a rational complete Segal space is. So my definition is, well, it's actually quite brief with the things that I've set up. So rational complete Segal space. X, well, it is a complete Segal space. It's a particular kind of a category up to homotopy. So it's a complete Segal space such that for every I greater than or equal to 0, if you look at xi, you look at the I simplicities, that's a space, but you ask it to be a rational space in the previous sense. Higher homotopy groups are rational vector spaces. And I am verifying in what I've done that this indeed models the structure of a category up to homotopy, where the mapping spaces between your objects are not just any spaces, but they're rational spaces, i.e. their higher homotopy groups are rational vector spaces. And also, the result that I've proven pertaining to these things, so this is from this year. I hope to have it on the archive soon. So the following theorem is the analog of Rezk's theorem for complete Segal spaces, but now I'm verifying that if you put the word rational, the argument, this line of argument works the same way. So in particular, I'm proving that there is a model structure, which I am denoting by fancy L sub Q. L stands for Lefbowski localization, CSS, on simplicial spaces whose fibrant objects are the rational complete Segal spaces. So whose fibrant objects are the rational complete Segal spaces, and the Cartesian property also survives. So also, that takes some verification, as is the case for complete Segal spaces. This model category is Cartesian. It is compatible with the Cartesian closure of simplicial spaces. So Rezk's argument carries in this rational complete Segal space setting. And this is good for like running technical arguments, this Cartesian property. And to wrap up in my last minute, I just want to mention some future directions, which is, I can say it in words. Well, there's other ways to model categories up to homotopy. And what I'm going to be thinking about for a big chunk of the remainder of my PhD is how to modify those models to also provide rational analogs that model categories up to homotopy that are enriched in rational spaces, and how to show that these other models are equivalent to the rational complete Segal space model. So really like this very nice line of argument for categories up to homotopy to provide a rational homotopy version of that for categories up to homotopy that are enriched not just in any space, but in rational spaces, in spaces whose higher homotopy groups are rational vector spaces. And that's all I had to say, and that's all the time I had. So thank you for your attention.
Thank you very much. Are there any questions?
Yeah, thanks. Do you expect that these rational complete Segal spaces should be using some kind of strictification able to be turned into categories enriched over differential graded algebras over the rationals? I would think that like if you had a category enriched over differential graded algebras over the rationals, that would give you like a very nice one of these where all the compositions were associative and so on, but you could still have interesting higher dimensional aspects.
That's a very good question. I'm meeting this week, I'm meeting someone who works very much in like strictification, and I will discuss it with them because it never crossed my mind. I don't have a good answer off the top of my head, but fortunately I know someone who's also interested in like sort of this kind of stuff. And I will pass it on to them, but that would be a very kind of that would be a very fun very fun direction. It would be very useful. But I haven't thought about this, but fortunately I know who to bounce ideas. I know a person that I can kind of bounce ideas with, and I will think about it. No, that's I don't have a good answer off the top of my
Okay.
head, but this is nice.
Yeah, I
Thanks.
think Julie Bergner would also know some stuff about that.
I'll definitely ask her as well. Yeah, that's I'm sure. That's very nice. Yeah. I haven't thought about it, but it's very interesting. Thanks.
Okay. Any more questions? Is there something in the chat?
I don't see anything.
All right, well, let's thank Eleftherios again.